It's been almost 2 years since I first published a video on special relativity, and about a year ago I finalized that series, adding up to 17 hours of video. Today we are going to do it in 17 minutes. Relativity is all about where things are at some time from the perspective of someone, and then taking that observation and try to calculate how that same observation would be for someone else. Well, the most famous relativity model, of course, is general relativity. It generalizes special relativity, which fixes everyday Galilean relativity. And today we are going to look at Galilean relativity, restricting ourselves to a single dimension in space, having objects only move at constant velocities, and those velocities need to be like normal, not too fast. And we will see that this model breaks down at some point, and then we can make the jump to special relativity. Here we see an animation. We see a gray woman doing a moonwalk sideways at 1.25 meters per second relative to the ground. The v is for velocity. We see a brown observer who moves at 1 meter per second to the right, and a blue one who travels at 0.5 meters per second. And these observers are obsessed with time and location. Therefore they have clocks and rulers, and they want to know where is the gray woman at any moment in time. So we are after the equation, what is the distance, the x-coordinate of the gray woman relative through the eyes of the blue observer. And the equation, of course, is that depends. It depends on the speed of the gray woman relative to the blue observer multiplied by the time it is when you look at the clock. And in this case, it's 0.75 multiplied by the time. 0.75 is the overspeed, the overspeed the gray woman has on the blue observer. And of course we can do this for the brown observer as well, and the overspeed there is 0.25. If you look at the relative velocities relative to the ground, you can probably come up with these equations. So this is Galilean relativity every day. So here we have these equations again. To calculate the overspeed, you can also pick a reference point, like the ground. If you subtract the velocity of the blue observer relative to the ground from the velocity of the gray woman relative to the ground, you get the overspeed of the gray woman with respect to blue. And you can also calculate it this way. How fast the gray woman is going from the perspective of the brown observer, and you can of course also calculate the relative velocity between the two observers. And time, well, time is time. Both observers sync their clocks at t is 0, time is 0, and they also sync their location. This is what we always do in relativity. You really don't have to, but then you get all kinds of constants in your equation which complicates things. So we sync them at t is 0. So this is Galilean relativity. What we're after, the core essence of relativity, is switching perspective between observers. So we want to take the readings of the blue observer and put them through some kind of set of equations, and calculate how the same observation would have been for the brown observer. This is what we call a coordinate transformation. So we're looking at what could be at the question marks. And I'm going to tell you in just a second, but if you want to do this on your own, just pause the video and see if you can come up with the question marks. Here we go. This is the outcome. The x-coordinate of the gray woman through the eyes of the brown observer is the same as the x-location of the gray woman through the eyes of the blue observer, minus the overspeed brown has on blue multiplied by the time you took the observation, you did the observation. And time, well, time is just time, and that's why there's a 0 in front of the x and a 1 in front of the t. This is Galilean relativity. So again, here it is. And I'm also repeating the overspeed equations here. Now the grey woman doesn't like to be chased by these two men who are obsessed with time and location. So we will turn her into Superwoman, making her go as fast as the speed of light relative to the ground. And if you then calculate the overspeed, you would expect to see this. C minus 0.5, because 0.5 is the relative speed of the blue observer relative to the ground, and C minus 1 for the brown observer. And here it is. All experiments that we've done so far tell us this is not the case. In both cases, the grey woman is moving away from the observers at the same speed of light. This makes totally no sense. This is completely irrational. And so no matter how fast blue and brown are running, even if they are running at 99% of the speed of light, Superwoman is still moving away from them at the speed of light. So we need a fix. Galilean relativity breaks down as these speeds. So mathematicians came in and they played with the coordinate transformation. They tried to find different things for the equation marks or the question marks. Here they are, a whole bunch of them. And yes, they came up with a new model that keeps Galilean relativity still alive, but at big speeds, incredibly large speeds, like the speed of light, the equation is different than Galilean relativity. And they considered it as a mathematical fix, not a theoretical reality. But then Einstein came in 1905, at the age of 26, and he said, well, let's just believe the experiments. Let's just assume that the speed of light is the same for everyone. No matter how fast you run to the light, away from the light, it's always the speed of light for you. And let's also assume that physics behaves the same for the different observers. And boom, he got exactly the same result as the model from the mathematicians. And here you see it, a snapshot of his famous paper in 1905. Einstein behind his old-fashioned typewriter, of course, typing in the solution. I will show you the solution in a more readable format on the next slide. But this is it. Now you look into the heart of special relativity. So this is the model we had, which breaks down and is being replaced by this model. If you look closely, the 1 in the upper equation is being replaced by a gamma factor. And this gamma factor is being defined with this equation. The second question mark also puts in a gamma factor. The third one as well, and the 0 in front of the x-coordinate in the second equation is being replaced by this. This factor is not called the Einstein factor. It's not called the special relativity factor. No, it's being called the Lorentz factor. In fact, the equations in green, which are the special relativity equations, are called the Lorentz transformation. And that's because Hendrik Antoon Lorentz, he's Dutch, so am I, had a huge contribution in the development of special relativity. Here is our Hendrik, he's Dutch, I'm Dutch, and I learned later he is born or was born in Arnhem. I was born in Arnhem, go figure. So that was nice to learn. Also, the overspeed equation breaks down, right? And if you do the mumbo jumbo with the equations, you can find out that this is the true equation, which holds for low speeds, but also for major speeds. And let's do the experiment. Here we have the two observers again. They are going to go head to head at 80% of the speed of light. So our normal brain would say the relative velocity between the two would be 0.8 plus 0.8 is 1.6 times the speed of light. But that's not the case. You need to use the second equation. And they will go head to head at 98% of the speed of light. Stuff becomes even weirder. if we make brown go as fast as the speed of light and you apply the second equation, you will find that the overspeed brown has on blue is the speed of light. This is really, really, really difficult. So no matter what blue does, running away or running towards the brown observer, the relative motion will always be at the speed of light. Now let's play with it. We have a model that keeps Galilean relativity alive for low speeds, but also deals with the speed of light or speeds close to the speed of light. And if you do some mumbo jumbo with the equations, we get time dilation. And time dilation tells us that time slows down when you are moving really, really fast. I'm going to repeat it. Time slows down. Physically. Really. This was so crazy they had to do the experiment. What they did is they took a bunch of atomic clocks, synced them. Some of them were left on Earth, others were placed in an airplane. They flew these clocks around the world several times, back and forth at high speeds, and then they calculated the time dilation from a theoretical point of view, and they checked it with the actual measurement. They had to use general relativity here as well, because gravity is involved. But the main point I want to make is that the actual observed delta time between the clock that went around the Earth and the one that stayed on Earth was about the same as the one calculated using the relativity models. A famous thought experiment is the twin paradox. One twin stays on Earth, the other one goes in a rocket, flies around the universe at high speeds, making her age less, making her time slow down, and when she returns to Earth, she will be younger than her twin. And here they are, Mark and Scott Kelly, an actual twin, both astronauts, and I think it was Scott who went on a space mission, spent many days in the space station, flew, and the space station flies at incredibly high speeds, and when he returned to Earth, he was younger than his twin brother. Go figure. Another thing that special relativity gave us is length contraction. Things shrink when you go really, really fast. Here in animation, we have an observer at rest with his ruler, and now we will see a blue observer at high speed, and you see that his ruler is much shorter than the ruler of the one who's not moving. So, moving stuff shrinks. Next level special relativity. You don't see this very often in videos online, almost like never. But if you want to make it real, you want to videotape these things, right? But if you videotape things, you have to take into account that you're actually recording light, photons, that hit the sensor of your eye or hit the sensor of your camera. And those photons took time to travel from the event to your recording device. So if you look at the stars at night and you see one explode, that explosion might have taken place many years ago because it took time for those photons to reach your eye. This thing is not taken into account in special relativity. But if you correct for it, things can become even more weird. Let's look at time dilation. Something traveling at 80% of the speed of light. Let's say a non-moving clock ticked for an hour. The moving clock will have ticked for 36 minutes. It is really what happens, while the observed clock only ticked 20 minutes. So you take a telescope from Earth and you watch and you record the clock on board of the moving object, and you will see that it is only 20 seconds. So yeah, this is so weird, this stuff, you know. So the non-moving clock goes round one time. The moving clock actually only ticks 36 minutes. And the one you videotape through your telescope only ticked 20. Length contraction. If you make this real world, also strange things really happen. We have a rocket at 80% of the speed of light. It's 25 meters long, and we are going to videotape a flyby. In real life, it will shrink down to 15 meters. This is what actually happens. But on video, it will look like the thing is 75 meters long. And as soon as it is passing us and flying away from us, it suddenly looks like it's 8.333 meters long. Also, approaching us, it looks like it's flying at 4 times the speed of light, and when it's moving away from us, it's only moving at 44% of the speed of light, while in reality, it was flying at 80% of the speed of light. So we can do this experiment. Actually, we can have this 25-meter long rocket fly through a shed with 2 doors. They are open. As soon as it is inside the shed, it's 50 meters long, right? So it fits the 20-meter shed. We can close the door, take the picture, open the doors and let it fly by. And this is what we are going to do. I'm going to open up 4 animations. In the top left corner, you will see what actually happens in special relativity from the perspective of the farmer in the shed. Below, you will find what actually happens from the perspective of the astronaut. But the astronaut and the farmer also videotape themselves using a long selfie stick sticking out of the shed or the rocket. And this is what they see. And I mean, it's just mind-blowing. Imagine Einstein meeting the astronaut and the farmer, and they both bring their videotapes to the table, and Einstein tells them there are 2 different realities which are both equally right. And then the farmer shows his videotape and the astronaut videotape. That would be a very, very special conversation. You can imagine that they will have to take the whole night to discuss this. So there you have it, special relativity in 17 minutes.